I go full screen mode, and now you should see my slides, and I will just close my image so I don't see myself when I'm talking. Okay, good. Thank you for inviting me. Thank you for the introduction. Yeah, so this afternoon I would like to talk to you about a paper that we have submitted on Tuesday about mapping hot and luminous stars in the Milky Way. And so before I start, let me just tell you what I mean by hot and luminous. In general, when I say hot and luminous, I intend massive stars and I intend young stars. And so I mean by hot and luminous, basically O and B type stars. So why are we interested in massive stars? So first of all, they dominate the interaction between the stars and the interstellar medium, and in our galaxy and in other galaxies. And in these two figures I decided to show, you can see the effect of the ionizing radiation coming from massive stars in a young massive cluster, in Cygnus on the left and in Orion on the right, in their surrounding interstellar medium. The second reason is that they are young, and so they still trace the spiral structure in our galaxy and in other galaxy. And in the second part of the talk, I will be focusing exactly on the spiral structure in our galaxy. And of course, they also not only trace the physical structure, but also the kinematics and the dynamics of the spiral arms. They are important because they drive the chemical evolution of elements in the periodic table. This is a periodic table for astronomers created by Jennifer Johnson at Ohio, where you can see all the elements in this periodic table that are color-coded in green are produced by the explosions of massive stars, for example, oxygen or aluminium and so on. And finally, I could not mention in this in a talk at Leuven that massive stars often, if not always, are born in binary or multiple system. I just wanted to briefly mention that, show you this figure from a nice paper by Ilva Rotbaya and collaborators. This is just the first figure where she explains, she describes very quickly the evolution of massive stars. And I just wanted to mention that massive star binaries are actually living sources of gravitational waves in the disk of the Milky Way and of other galaxies. So I hope you have convinced you that it is important to study massive stars for a number of reasons, and that's why in the SDSS we are devoting a large fraction of observing time to have a survey of massive stars in the Milky Way. So for those of you who don't know what is SDSS 5, in SDSS 5 is a survey that is about to start, and we will get spectra, the spectroscopic survey, multi-epoch spectroscopic survey in the optical and in the infrared of the Milky Way and local volume galaxies. And you can find more information in this paper by Kohlmeier 2017, 19, and Blanton 2019. So, as I said before, we have a program in SDSS 5 that consists of observing ONB stars in the Milky Way and in the Magellanic Clouds. And this program was devised to obtain a census of massive stars, a spectral census, so effective temperature, gravity, masses, abundances, to study their multiplicity and binarity property. Of course, I cannot avoid mentioning astroseismology, although I'm not at all an expert in astroseismology, but I'm sure there are people in the audience who know much more than I do about it. And I'm interested in ONB stars and observing ONB stars, taking spectra of these stars to map the young Milky Way, and in particular to derive the recent star formation history of the Milky Way, and to derive the kinematics and the dynamics of young massive stars. I now want to speak briefly about how we selected our sample. So as I said before, We want multi-epoch observations. In particular, we are aiming for 3 epochs, and we are aiming at getting spectra, visible spectra with VOS, which is a low-resolution spectrograph of stars brighter than 16. And to select them, we mainly used 2 criteria. The first criterion is a criterion in the luminosity in the infrared in the 2 mass K band, and in particular we are selecting stars that are brighter than 0, and these roughly corresponds to stars that are of earlier type than B7b. And the stars brighter than 0 are displayed in this color plot in J minus K versus Gaia BP minus RP. And as you can see, it is quite easy, relatively easy, to separate them from bright giants. And so by applying cuts in the optical and in the infrared colors, we can select stars that are consistent with being OND stars, and also that are quite reddened. The sample is shown in this plot. So you can see that most of our sources are distributed in the galactic plane, and that they are disk stars, and some of them are also in the Magellanic Clouds, and the target list consists of around 1 million sources. So now, I said before that this talk was focused on mapping the young Milky Way. So for sure, I was not the first one to come up with the idea of mapping the young Milky Way with massive stars. And I think the first paper in this context was written by Morgan and collaborators in 1953. So Morgan took spectra of of O-type stars and early B-type stars and derived distances to these sources. And he noticed that O and B-type stars were not uniformly distributed in the disk of the galaxy. So in this figure, you see the disk of the Milky Way as seen from the top. The galactic center is here, and at the time it was thought that it was around 9 kiloparsec from the sun. And you see that apparently O and B stars are not uniformly distributed around the sun, but seem to follow a certain pattern. In the same year, Oort, Van der Hulst, and Muller firstly studied the 21 centimeter radiation from hydrogen, and again tried to picture the distribution of neutral hydrogen in the galaxy. Again, this is a figure of the galaxy as seen from the top. The center is here and the sun is over here. And you see that the black points correspond to points where the emission from the 21 centimeter has a maxima, and instead the empty dots correspond to minima in the 21 centimeter emission. And again, they, for the first time, proposed that they were observing the spiral arm structure of the Milky Way. The fact that the Milky Way has spiral arms and has 4 spiral arms was first proposed by Georgin and Georgin in 1976. They studied H2 regions. So H2 regions are usually related to star formation. They are massive star formation. And again, they fitted the distribution of H2 regions in the plane and proposed for the first time that indeed the Milky Way seemed to have 4 main arms. And this view had a discrete success, and it is what in general we think when we think about the structure of the Milky Way, and in particular the number of spiral arms. We tend to fit for example, the distribution of masers in high mass star forming regions with 4 or 5 spiral arms. And these spiral arms going from regions the closer to the center to the outskirts are Scutum, Sagittarius, the local arm, which is for some people a spur, so not a main arm, or for other people is it actually a prominent arm. then the Pierce's arm, and finally the outer arm. And this figure shows again a view from the top of the Milky Way disk. The galactic center is here, where the red cross is, and then the sun is over here. And these points are from Reed et al. In 2019, and as I said before, they correspond to masers in high mass star forming region. And of course, in recent years, also new observations of the H1 emission were performed. For example, this is a famous figure from Levine et al. 2006. And again, the maxima of the emission are displayed with the orange color scale. And I have to mention more recently, the Thor survey is producing results at very high angular resolution, and again pushing our resolution and our understanding on how of the distribution of atomic hydrogen in the Milky Way to further and higher precision levels. So I've spoken about hydrogen, I've spoken about massive star-forming regions. Another tracer of the Milky Way structure is dust. And I want to mention here these two work, this work by Driemel and Spergel in 2001, and also another paper by Driemel 2000. And in this work, they propose something interesting. They propose that the dust that again traces young stars, traces the young disk, could be described, with 4 spiral arms. In this paper, where they compared the dust distribution with the K-band emission, and the K-band emission traces older stars. And they proposed for the first time that the distribution of dust could trace 4 spiral arms, while the distribution of older stars could better be described with only 2 arms. And so they proposed that there are 4 arms in young stars and dust, and 2 arms in the older population. Then Gaia came in, as you are all aware of. 25th of April 2018 was a very special day for many people, and many people, at least 3 different groups, but probably many more, tried to map once again the dust distribution in the Milky Way disk. So again, I'm trying to show you plots always in the same scale. The sun is always at the center of these plots, and the galactic center is somewhere in this direction, so towards the right, at around 8.2 kiloparsec. And this is the dust distribution inferred by using the Gaia inferred distances to obtain distances to the dust clouds. And what is it interesting to note, I think, from all these studies, is that the dust distribution is not uniform, it's very patchy, and it is very hard to draw the spiral arms by using this data. And one problem is that the dust distribution is patchy. The other problem is that we are just seeing a limited fraction of the Milky Way disk. We are just probing at 3 or 4 kiloparsec around the sun. And that is a problem because it's difficult to infer the global structure of the Milky Way from just observing a very small volume of the disk. So this is for the dust. There were also a few papers, this one in particular by Chen et al. 2019, where they use OMB stars, again, to try to study the structure of the Milky Way. And so they devised a sample of 14,000 stars, almost 15,000, combining BFAS and Gaia DR2. And again, they were the first proposing that among the first proposing that the spiral structure of the Milky Way could be described with flocculent patterns. So now, for many of you, or maybe for 1 year ago, at least for me, flocculent was a very weird term, and I didn't know what it was. And so I did some research, and I discovered that spiral galaxies can be divided, let's say, in two subsamples, flocculent galaxies or grand design galaxies. And so as you can see in these two pictures, in flocculent galaxies, there is no clear sign of a spiral pattern, while in flocculent galaxies, in grand design galaxies, there is the spiral arms are very prominent, and it's very easy to see them in gas and young stars and older population. As I said before, we just observe a little fraction of the Milky Way stellar disk. So now I would like to play a little game, and so that you understand better the situation we are in with our amazing set of data, which is still a set of data which we use to observe just a fraction of the disk. I want to play a little game, and I want you to tell me, by seeing just a fraction of a disk of a galaxy, what do you think this galaxy, this spiral galaxy is, if it is a flocculent or a grand design? So I would like you to raise your hand, or at least your virtual hand, if you think that this galaxy is flocculent. And maybe Joris can help me and tell me how many people think this galaxy is flocculent. And don't be shy.
At the moment, I only see one person who thinks it's flocculent.
Okay.
Or two persons, sorry.
Okay. And then who thinks this is a grand design?
I see at least 3 persons.
Okay, so this one is NGC 7793, and it's a flocculent galaxy. Okay, let's have another try. And people, please don't be shy. This is just a stupid little game. So what do you think? Is this flocculent? So raise your hand if you think this is flocculent.
I don't see any hand for flocculent, actually.
And then, okay, and then who thinks is a grand design?
I see at least 7 hands, I think.
Okay, so
it's a clear winner.
This is MA3, this is a grand design galaxy. So I hope I've convinced you that deciding whether a galaxy is a grand design or a flocculent galaxy just by seeing a fraction of the disk is not that easy. So let's get back to the topic. What do we need to map the spiral arms of the Milky Way? As I said, we need a sample of ONB type stars, and we have that sample, and we need distances. So as you might be well aware of, Gaia measures parallaxes, and distances need to be estimated. So if the parallax is good enough, in general, that is not a problem. So you can just invert the parallax and obtain a good estimate of the distance. However, as Corinne Baylor-Jones says, if your error are larger than 20%, then estimating distances is an inference problem, and you need to use priors. And so in this paper, we devised a model that was used to reproduce the properties of our data in terms of spatial distribution, luminosity distribution, and we also tried to include the information from proper motions. And in particular, we assume that stars in our sample follow galactic rotation, and so should have certain proper motions that we can compare with the observed ones. But I'm not gonna go in any detail on this, and so if you're interested, you can ask me questions later on. And by doing so, by obtaining distances, we can obtain a density distribution of sources in the galactic disk. And this is what the density distribution looks like. So here the yellow, light yellow contours correspond to regions with low density, and the dark regions correspond to regions of high density. There are many features that one can see in the distribution of O and B stars, and I will start by describing the features at the center of the map. So at the center of the map, there is the sun, and you can see that the region surrounding the sun is quite empty. And this is because of at least a couple of reasons. First of all, the region surrounding the sun is filled with ionized gas, and it is a structure that's called a local bubble. And so there was not much star formation happening in the last 50 million years, probably in the 200, 300 parsec around the sun. Further, our selection is based on the combination of Gaia and Tumas, and both Gaia and Tumas are incomplete at the very bright end, and so we are probably missing sources that are bright because they are nearby. Then you can see that the dense clump correspond to very well-known star-forming regions. For example, Orion, Vela are within 500 parsec, and then there are massive star-forming regions such as Cygnus, Vela, OB, the other one, Carina, and then other massive star-forming regions towards Scutum, Sagittarius, and so on. Here, these structures seem indeed to trace the spiral arms, and these and the density of the sources is really high towards the galactic center. So as a reminder, the galactic center is towards the right at 8 kiloparsec. But it is not easy, as I said before, to recognize spiral arms in this sort of plot. And further, the density along what one may think is a spiral arm is far from uniform and is characterized by underdensities and overdensities, and also by these gaps that were recognized in other studies. Finally, there are radial features, and these radial features are due again to a combination of factors. And first of all, we can see things through, so first, the farthest things that we can see we can see them because we can pierce through the dust. And so in some region, we can see through nearby clouds. In other regions, we cannot pierce through the dust. And so in some regions, we tend to see farther stars than in other regions. These are called shadow cones produced by foreground extinctions. And of course, above 2 or around 3 kiloparsec, distance errors start to become important and starts to become significant. And the effect of parallax errors and therefore distance errors is that stars tend to move along the radial direction. We can compare this map, for example, to one of the dust maps that I've shown a few minutes ago. This is the same map as before, although now it is in grayscale. And the map shown with the purple color map, yellow to purple to pink color map, is the map produced by L'Allemande et al. In 2019. And here, I think the interesting thing of this plot is that the dust and the stars are offsetted with respect to each other. And this is something expected because after they are formed, stars will move away from their birthplaces, they will disperse, and they will start following galactic rotation, while the spiral arm pattern moves at a different speed. So it is expected, but it's still nice to see such a clear offset between stars and dust. And we can also compare our distribution, for example, with the distribution with the masers and the spiral arms positioned by Reed et al. 2019. So in this plot, again, the grayscale represents the distribution of OND stars, and the dots correspond to the masers, while the lines correspond to the fit to the spiral arm positions, and their thickness is proportional to the width of the spiral arm. And again, with the single masers, distances and positions, there is a good agreement between our overdensities and the masers distances. However, if you then look at the fit for the position of the spiral arms, the discrepancies become more evident, and in particular in this region where there are no data. And here you see that the inclination is clearly quite different from what is inferred with the masers position. Okay, so we are towards the end. In this talk, I've been talking about our selection of ONB type stars, and I described how we use this sample to study the spiral arm structure of the Milky Way. So I say that the distribution of sources in the plane of the Milky Way is substructured, characterized by over and under density, and then the over densities correspond to star-forming regions such as Carina, Cygnus, and Cassiopeia. And then I noticed that the inner arms their inner arms are more prominent than the outer arms. I mentioned at the beginning that we are getting spectra of these sources in the context of the SDSS-5 survey, and the information from the SDSS-5 survey will be crucial because at this point we are only studying the space distribution of massive stars. We are not studying their kinematics and we're not even thinking of studying their dynamics. But with SDSS, such studies at least will be finally possible, and this will be of extremely high importance to understand the nature of the spiral arms. So I can stop here, especially if there are questions. Or I could go ahead, I can talk a bit more about how can we improve this and like future developments of these kind of studies. Or I can talk a little bit more about distance determinations, but I would say I would stop here and I will be happy to take questions. And of course, you can also ask me about what I plan to do in the next few months after we get data. So for now, thank you for your attention.
Thank you very much. Very nice. I'm sure there will be questions. So if you can put or show or tell in the chat that you have a question, and I will say your name. Dominic, please. You're the first one.
Thanks very much, Eleonora, for a great talk. Can you go one slide back to your overlay of the spiral arms? Mm-hmm. So I noticed there's a kink in the Sagittarius Carina arm. I've never actually seen that before. Where does that come from?
It comes from Reed in Reed et al. 2019. I don't know exactly, so I don't remember exactly why they decided to put a kink there and like what. But I think it's because they want to fit both these positions and also these maser positions. So I think it must be something related to how they put sources in different arms. So they, of course, they decided that some masers are in one spiral arms and some other masers are in other spiral arms, and then they try to fit their distribution. And I think the kink comes from that fit. But it is in their paper.
Okay, that's great. Thanks very much.
Anyone else? Maybe I would like to take the opportunity to ask a question myself. How do you determine because for example, in this figure, how do you determine the uncertainty related to the density maps? because this is something that I also sometimes need, and I actually don't know how to do that. So do you have any idea how to do that?
Okay, so I haven't done that in this paper, like determining density uncertainty. I think in principle, one way to do that would be probably to do something like Monte Carlo sampling or something of the distances, because the distances, of course, have uncertainties, right? And so you, in principle, could do, I don't know, a certain number, like 10,000 realization of the density, and then measure an average and some dispersion around this average. But I also, I haven't done it for this paper. Mm-hmm. But okay. It's something that I would think of doing it in that way. But I would be happy to chat more about that.
Okay, thank you. Simon, you also have a question?
Yes. Thank you, Eleonora, for a very, very nice talk. I have a question also about, if we stay on this slide. You mentioned those streaks that you see, and you said they were related to foregrounds.
Yeah, sorry, I said that very badly. So these features.
Explain it again, because I wasn't sure if you did.
Yeah. So you mean these radial features?
Yeah.
So okay, so basically we have a foreground dust, and in some regions you can see through the dust and see stars that are more distant than in other regions. So for example, here we can probably in general see farther stars than here, for example. However, and so this is one of the reasons why there are these features. But of course, another reason is that distances have errors, and the errors tends to move stars along in the same line of sight. I don't know if that's clear. So it is a combination of distance uncertainties and the fact that we can see if we can see or not through the dust.
Okay, thank you.
Connie, please.
Hi, Eleonora. Thanks for your talk. As you can imagine, I have an astroseismology related question, and I am an expert, but it's a general question.
Okay.
How important or how useful is a good age determination for you to understand your dynamical properties?
Oh yeah. So it is very. The short answer, yes, it is useful, because one of the biggest problem at the moment is that just with photometry, we cannot really say if a star is maybe on the main sequence or just evolved outside of the main sequence. And so having ages and actually having spectral types would already be a huge improvement, because it will help us remove contaminants from this sample. And contaminants for us are, for example, A stars. But having ages, having spectral type would be really helpful in cleaning the sample, first of all. And then the more precise ages we have, the better it is in understanding the kinematics and dynamical properties of different populations with different ages.
Okay, so a factor 10 age a factor 10 uncertainty in age is already useful, but the factor 2 is better. Is that a good translation?
I think it is a good translation. I would say ages in general, having ages would be great. Having precise ages would be even better.
Thank you.
Yes, Ilya, please.
Hi, Eleonora.
Hi.
So in this plot of the density, I see two bubbles free of dust. One is where we are, and another one is a little bit on the left.
Here.
Do you have any idea what causes the appearance of these bubbles?
Yeah, so especially this one was already reported, and it's called something like Perseus gap because it is in the Perseus arm. And the most common explanation is that a star formation event happened there, and massive stars swept away gas in that region, creating that sort of gap. So for this gap or bubble here, and also there is something that hints to the presence of a bubble also here. For the region surrounding the sun, again, I said that a little quickly before, but it's probably a matter of the fact that we are incomplete at the bright end of our sample, because 2-mass photometry is not great at the bright, when stars are bright. So which means that for nearby stars, we don't have great photometry, and in general we remove those sources. And also Gaia is not super complete at the bright end. And also, in general, there are very few massive stars, very massive and very young stars around in the solar neighborhood. Because again, there was not that much recent star formation in the region surrounding the sun. Recent and massive star formation in the place that's called the local bubble, that is more or less centered in the sun, and it is a cavity, let's say, full of ionized gas, but without much molecular gas. And so it is these two, for the local bubble, it is these two reasons combined, and then in the other regions it's because of star formation, basically.
And I would guess that these bubbles, they do not stay there forever, probably because the galaxy is rotating. And do you think they will disappear at some point in the future?
I guess so. I don't know exactly what would be their duration, their lifetime. But yeah, I think at some point stars simply disperse in the field, and so they tend to fill the gaps. Yes.
Okay, thanks.
Anyone else a question? Okay, I'll ask another one actually. What will you do as soon as DR3 arrives?
Rerun everything.
Rerun. You expect large changes?
So the parallaxes will be better by 20%, Anthony says. I trust Anthony. So I will not expect dramatic changes, but I would hope for a partial, at least, resolution of these radial features. So I will run everything again because of the target selection of the SDSS file. So that's why I will run everything again. And if the referee doesn't ask to do it, I will not ask. I will not do everything again for the paper. But I have the feeling the referee might ask.
I think so. Anyone? If not, then I would like to thank Eleonora again. Thank you very much for this wonderful talk. So for those among you who are interested in joining us for a coffee break, coffee break with our speaker, please stick around. So fetch a coffee, fetch a tea.